So, a little bit of a definition. We already talked about this, and the word span did come up. Stephen is all hall pass. Okay, Stephen. Okay, 5 minutes, please. A set of vectors that is used to generate any vector in R squared is called a spanning set for R squared. Okay? Simplest one is the ij vectors, which we've already covered. There's an infinite number of spanning sets that you can form. So u and v. So we're saying that u, vector u, is not the I vector and the j vector. The v is not the j vector. We're saying just arbitrary two other vectors can become spanning sets as long as, and here's a condition, that u is not some scalar multiple of v. U and v are not collinear. You can't create the v vector by just simply scaling the u vector. That's the point we're making. If you can, then it means that it cannot span the entire space that you're trying to span. Similarly, in R3, so in 3 space, the simplest spanning set we said was ijk, but you can also come up with any 3 vectors, well, not any, because there are some conditions as well. You can come up with 3 other vectors, not the I, j, and k vector, not those unit vectors which sit on each of the axes, but you can come up with 3 vectors as long as one of the vectors cannot be created by just simply adding together scalar multiples of the other 2. That is to say that the u, v, and w vectors are not coplanar. You could not, the 3 tips of those vectors, right, the 3 heads of those vectors don't sit on the same flat surface, right? That's what we're saying. Because if they do, then they cannot span, right? Remember, 2 vectors can span a plane. A third vector, if it's sitting on that plane, doesn't add anything, and you saw the graphic that he was using a while ago, doesn't add anything to the span. It just means you're still sitting on that same plane. Okay, I'm hoping that all makes sense so far. So here's what we're going to do. We're going to write the 519 vector as a linear combination of 4 minus 1 and 1 minus 7, and also a combination of minus 2, 3, and 20, 23. What does that mean? Well, I'm going to try to describe it to you this way. We want to take a scalar, put it on the vector, the 4, 1 vector, this one here, and put it on this vector here. When I add those two together, I want to end up with this vector right here. That's my goal, right? Multiply the first vector, the 4 minus 1 vector, and the 1 minus 7 vector by some number and make that become the 519 vector. Now, as long as those vectors are not collinear, it should be able to be possible. So what we're saying is that we're trying to make these vectors here become like basis vectors. No, that's not the I vector. That's not the J vector. Neither of those is the I or the J vector. But I'm still saying that I can reach to that 519 vector by multiplying some, by finding some scalar to multiply by these two and make it become that 519 vector. I'm also saying that it may be possible for me to take these two vectors and do the same thing, right? We're going to try the 4 minus 1 and the 1 minus 7 first. In fact, I'm going to let you do the second one, but let's try the first one first. Let's see if we can multiply the 4 minus 1 and the 1 minus 7 by some scalar and make it become the 519. All right, so here we go. So I'm going to take A. I don't know what A is yet. All right, we'll get to that in a minute. We're going to take some scalar and multiply it by the 4 minus 1. So this vector here. We're going to take some scalar. Now remember, this is not I, this is not J, right? Which is what we're accustomed to, the 1, 0, and the 0, 1. That's not what this is. I'm going to multiply the A by the 4 minus 1 and the B by the 1 minus 7, and I'm going to make it become the 519. Is there a way that we can figure out what those two vectors, sorry, not what those vectors are, what is that A and that B that will make that magic happen? All right, so how does this work? Well, this A multiplied by the 4, right, plus this B multiplied by the 1, so the two x coordinates, the x coordinate here is the 4, the x coordinate here is the 1. Well, this 4 times this A and 1 times this B should give me my new x coordinate, which is 5. I'm hoping that makes sense. All right. Secondly, if I'm looking for my y coordinate, the same scalar of a multiplied by -1, so minus a, and the same b multiplied by the -7 should give us the 19. So look at that. That looks familiar. 4a plus b is equal to 5, and minus a minus 7b is equal to 19. I want to make sure, though, that before I go any further, that the way I set that up makes sense. Right? Let me check in with the room on that a little bit, just to get a sense of whether people are okay with that. Let's see. Carly, what do you think? Could you go with the bottom one? I sure can. Carly, but okay, all right, tell you what, before I ask Carly, let me go over that again. I'm taking, remember, to get the sum of two vectors, and we've done this before, Ashfan. We just added together the two x's and the two y's, and we got what the sum of the vectors was. Right, Ashfan? Remember us doing that before when we were doing this a couple of days ago? Okay, so, but now we're saying there's a scalar that we want to scale the first vector by, and a scalar we want to scale the second vector by. We're calling the scalars a and b, so that's what the a and the b represent, two scalars. I want to scale the first vector by multiplying it by a, and scale the second vector multiplying by b, and end up with that 519 sum, because it seems as if I can combine, Ashvan, the 4 minus 1 and the 1 minus 7 and get the 519 third vector, right? It seems I can do that. If I just find the right a and the right b, it sounds like that could work, is what I'm saying. All right, so here's what I did. I took the a and multiplied it by the 4, right? Because that's my x value there. So I'm scaling the x value, which is what the 4a is. I'm scaling the other x value to give me the final x value of 5. That's where the 4a plus b giving me 5 came from. I'm going to do the same thing for the y value now. My y value needs to end up at 19. So if I take that same a and multiply it by this y value of -1, and that same b and multiply it by this y value of -7, hence the -7b, I should get the 19. Does that kind of make sense to you now, Ashfan? Just wanted to check just to make sure. Okay. And I was about to ask Carly. Carly, are you with us? Is this all making sense to you, Carly? Okay, perfect. And it makes sense, right? Or are we not sure? Are we good with that? Okay, good. All right. So when you look at that, what does that kind of say to you? Can this be solved? Can I get the A and the B from what you see there? Is there a way that we can do that? Right? Have you done math in the past? Maybe grade 10, maybe, that allows you to solve this substitution elimination. Thank you, Richard. Right? Does everybody accept what Richard just says? This can be solved by either substitution elimination. And I'm going to go through that process with you right now. Just remind you, for those who have forgotten how this works. I'm going to use elimination. You can use substitution if you find it easier. So the way I do this is I try to get the two things to match. So here's what I'm going to do. I'm going to take the second function and multiply it by 4, right? Why am I doing that? I'm multiplying everything by 4, by the way, the whole thing by 4. So I'm doing that because I'm trying to make the A's match up, right? If my A's can match up, then according to elimination, I can either add or subtract these from each other. So I multiply the second equation by 4, everything in the second equation, which gives me my new equation, which is this, minus 4a minus 28b equals 76, right? You can check the math on that, make sure I did that right. Now I'm going to take the first equation, bring that over, and now I can add these two together, right? And how elimination works is, if I add them together, it means that the 4a and the minus 4a, when I add them together, disappear. The b plus the minus 28b gives me minus 27b. The 576 gives me 81. Okay, just follow the math on that, right? And therefore, I can now solve for b, which gives me minus 3. Okay, so once I do that, what do I do next? All right, all I have is b. I need to get b and a, but I only have b. What am I supposed to do with that? Right? All I have is b right now. So Adam says solve a with b equals -3. So, okay, good. So I'm going to do exactly what you just suggested. So I'm going to go ahead and do that. Well, I kind of skipped a step. I'm just going to put b equals -3 into the first equation. So it's 4a, excuse me, -3 equals 5. So that would mean that, in fact, I'll just do that quickly over here. So 4a, and the b was -3, so minus b equals 5. So that means that 4a, what is that? Minus, yeah, sorry, that's wrong. Let me fix that. It was 4a -3. Sorry, -3 is equal to 5. So that means that 4a is equal to 8, and therefore a is equal to 2. Okay, so that's what I've done. That's all I've done. Just subbed it back in. Thank you, Tom Leo and Thomas and Adam. Okay, so now I'm ready to do what I wanted to do all along, which is to show that I can write, go back up to the top where they asked us to do, write 519 as a linear combination of 4 minus 1 and 1 minus 7. So if I take the 4 minus 1 vector and multiply it by 2, because that's my a, right? I was trying to use I was trying to figure out what a was. I figured that a was 2. So 2 times the 4 minus 1 minus 3 times the 1 minus 7 is equal to the 519. Okay, which is exactly what I was asked to do. So I've done it, right? So I've used not the I and j vectors. I didn't use that. I used two arbitrary vectors. I used the 4 minus 1 vector and the 1 minus 7 vector, and I was able to, with scalars, create the 519 vector. Okay, I wonder if you could do the same thing. And that's what I'm going to turn things over to you to do. I'm going to erase my garbage here, get rid of this stuff here. Right? And I'm going to erase this as well. And I'm going to say to you, I'd like you now, everybody, to try to do the same thing to get the same 519. So let me come back to this here. Let me show you what I'd like you to try to do. And I'm going to tell you right now, the answer is not going to be a nice, simple number, like a whole number. It may be a fraction, so don't be scared when you see a fraction coming up, right? I want you to get the same 519, but I want you not to use these two values. I want you to use the other two values as a combination of -23 and 2023. So get your papers, get your pencils, whatever it is that you write with, your crayons, I don't know what you write with. I want you to do exactly what I just did. Get a different value of a and b this time, but combine the -23 vector, the -2023 vector, and get the 519 vector. So you're going to change this and this. You're going to put in its place the -23 and the 2023. And at the end of the day, so you're turning things over to you now. At the end of the day, I want to see you set out a combination of these two vectors, the -23 vector and the 2023 vector, and it's going to be equal to 519, but with different a's and b's, different scalars on them. Okay, I'm going to put myself on mute for, well, maybe not on mute. I'll stay here just monitoring the classroom. And I'd like to see you do that right now. Okay, so here comes the calculation. Same thing, A -23 and B is 2023, right? And I'm going to go through the process again. So -2a plus 20b equals 5, 3a plus 23b equals 19. And then what I did in my case, I'll tell you what I did, is I multiplied the top one by 3, okay, the top equation by 3, and I multiplied the bottom equation by -2. You see, if I need to spend more time on solving linear systems, then we can certainly do that in the afternoon session after class. But it's the kind of thing that I expect you to be able to roll with. So one way to solve a linear system is to multiply the top equation by the coefficient of the second equation. So I did that by saying the top one by 3, the bottom one by -2. That's what I did. I'm not sure what you did. I'm not sure how other people got their answers did it. And then the top equation becomes -6 Of course, everything gets multiplied by 3, by the way. So 3 times minus 2, 3 times 20, 3 times 5 gives us this. The bottom one by minus 2 gives us the same minus 6 again, right? And that's good because now we can subtract the two equations from each other, right? The first time I added because both of them were opposite signs. But now I'm subtracting. So if I subtract, I get that 106b is equal to 53. And therefore b is equal to 1/2, which is what a lot of you got. And again, I'm going to put that half into the function back, and I'm going to get 5/2 as the result of that. Okay? All right. So again, I'm sort of suggesting or recommending that if you're not 100% sure how to do this, that you need to spend some time going over linear systems, sublinear systems. Come see me if you want some help with that. I'm fine with that. Okay, so here's the equation. 5/2 is my A, times the minus 2, 3, plus a half, 20, 23 gives me that 519. So we've just basically still been able to come up with a linear combination of two completely different vectors, apart from the first ones, the 4 minus 1 and the 1 minus 7, and still we're able to give us the 519, right? Different scalars, but the same result. Okay, let's move on. Now, show that these two vectors cannot span R squared. Why is it? Can anybody look at these two vectors? One is the 2, 3 vector. Right? I should have used square brackets on that. And the other one is a 4, 6 vector. And I'm saying they cannot span R squared. I cannot take these two vectors and create some other vector, any other vector that I want. Can anybody tell me why that is? Does anybody see a reason? They'd be on the same line. Sarah is right. In fact, you can say the easy way to figure that out is to divide the ratio of your x's and divide the ratio of your y's and see if you're getting the same thing. If they're equal, in this case, the ratio of the x's would be 2/4 and 3/6. Both of those are equal to a half. So it means that they cannot span R squared. They're collinear, right? They're on the same line. Sarah said it best by saying that they're both on this. One is basically just twice the length of the other, but they're sitting on the same line, right? The same, they're going in the same direction. They're running on the same. I don't have to go in the same direction. They're going in the opposite directions. You still couldn't span the R. You couldn't span all of R2 because they're just simply collinear vectors. Okay. Now, let's see how much time we have left. Let's get to 3 space now. Consider what happens if we try to write a vector in R3 as a combination of two non-collinear vectors in R cubed, right? So now we're thinking, again, I know that sometimes it's a little harder to come up with or to imagine yourself in a three-dimensional world without actually, on a flat surface. So that's a bit of a challenge. And worse when you have a teacher who can't draw, just has that doesn't have that in his DNA whatsoever. So if I made one vector ABC, just 3 numbers, and the other vector DEF, and we wrote a third vector by adding scalar multiples of those two vectors, right? So if you see where I'm pointing to here, then the W would, of course, be R times all of the letters in the first one, plus T times all the letters in the second one, and then you combine them together into one vector. Now, if you look at that, you might think that W would be virtually any vector in R cubed, this new vector, this vector that you've created. But that's not the case, because this new vector that you created by just summing the first two, again, think of this in 3 space now. That new vector that you created, they're going to be vectors on the same plane. So if you create a third vector from summing those two vectors, guess what? That resulting vector will also be on the same plane. So if you can create a third vector by just simply scaling two vectors in 3 space, the third vector that you've created would just be, as it says here, the third side of a triangle formed by drawing those vectors, and you would end up with just simply a plane triangle, a plane figure, a triangle sitting on a plane in 3 space. Hopefully this doesn't sound like Greek to you. Hence, the set of UV spans a plane in R cubed. I cannot span all of R cubed. I can span a plane, in R cubed, I cannot span all of R2 in its three-dimensional glory. I can only span a plane if I have only two vectors, okay? So here's what we're going to do now. We're going to determine, this is the thing that I want to make sure we have enough time for, 20 minutes. We're going to determine whether these three vectors are coplanar vectors. So we have three vectors here, the 3 minus 1, 2 vector, the 9 minus 5 minus 11 vector, and the minus 1, 1, 5 vector. Are they coplanar? Do they all sit on the same plane? Well, here's how we're going to know if they're coplanar. If I can take two of these vectors and create a third vector, that means they're coplanar. Let me say that again. If I can, and it doesn't have to be these two, if I can combine any two of these vectors by putting scalar multiples on, let's say B and C, and that will give me A, if that is possible at all, then these vectors are coplanar. If there is no way to combine these two vectors and get the third vector, it means that these are all independent vectors. That's what it means. So I'm going to walk you through the process now to determine whether these are coplanar vectors or not. Can I somehow take two of these and create the third one? So let's set this up. I'm going to say there's an A that I'm multiplying by the first vector, the 3 minus 1, 2 vector, and a B that I'm multiplying by the second vector. And I'm going to see if I can make that equal to the third vector. I'm going to try this, see if this can work. All right? So we're going to do what we've done before. I'm going to take 3 times A plus 9 times B. All right, hopefully this makes sense. 3 times the A, 9 times the B, and set that equal to the minus 1. I'm going to take the A and multiply it by, so this is now the Y coordinate. A times the minus 1 plus B times the minus 5, that should give me the Y coordinate in the third vector, which is equal to 1, right? So already we have a way with two equations to be able to solve for A and for B. I'm not going to turn it over to you because I don't think we have time to do that today. I'm going to walk you through the steps of getting that A and that B. So what I'm saying is that I'm only going to try to take the X coordinate and the Y, not the Z coordinate. We're going to use the Z coordinate to see if this works or not. We get to the Z coordinate later on. We're going to take the X coordinate. So we're going to take the 3A and the 9B and set it equal to the X coordinate of minus 1. I'm going to take the minus A and the minus 5B and see if I can get that equal to 1. We're going to leave the last one for now because that's going to tell us whether summing these two together will give us this one completely. We're not sure yet, right? This is just a test now. So let's see if we can solve for A and for B. So we'll go through the process again. I'm going to, the third vector that we could get from this is the one we're going to leave aside for now, 2A minus 11B. So 2 times A plus minus 11 times B should give us the 5, right? So that's going to be the test. That's going to be the check. All right, hopefully everybody is on the same page with me here, right? We're only going to use these two, then we're going to check to see if the third will work. So let's go ahead now and multiply the bottom equation by 3, and we've done this before, so hopefully this is going to make sense. Bottom equation by 3, right? And what am I trying to do? I'm trying to make it match the top equation. So that becomes this equation, minus 3A minus 15B equals 3. So 3 times all of these components here gives us this equation. And then I'm going to take the top equation and just simply write it again. There's no point in me changing anything there. It would be on the same. Oh, that was a comment from before that Sarah had. So now we're going to go ahead and am I going to add these or subtract these, by the way? Just let me just check in with you on that. What do I do with this set that I have here? Do I add or subtract this time? Folks, help me out here. I'm going to add, right, because I have opposite signs, right? Just like what we did on the very first one, we're going to add this one together, right? The A's are going to cancel out. Those are done. They're gone. The 9B and the minus 15 gives us minus 6B. Excuse me. Again, check these for yourself. The minus 1 plus a 3 gives me a B value, sorry, a value of 2. So, of course, I'm going to go ahead and solve for B at this point, and I'm getting minus 1/3. Okay. Again, I'm assuming that everybody knows how this works. So I'm going to go ahead and calculate my A value. See, folks, fractions shouldn't scare you, right? That's a part of doing math in grade 12. It doesn't always work out to be a nice, neat number like 6 or 52 or 19. Sometimes you got to work with fractions. So the A works to 2 over 3. And again, just so that we're clear on where that A is coming from, I'll do a quick calculation here, even though we're running out of time. So we have two equations, 3A plus 9B equals minus 1. So what I'm doing is I'm saying if B is minus 1/3, I'm going to say 3 times A, right, plus 9 times, where's my B value? Minus 1/3 is equal to minus 1. Okay, I'm just substituting that into the equation. So 3A, now 9 times minus 1/3 should give me minus 3 equals minus 1. And then all I have to do now is add that 3 to the two sides. So 3A is equal to 2, and that's where the A of 2/3 comes from. All right, just thought I'd make that quick point there. So what I'm going to do now is I'm going to say, okay, so I have an A and a B. How does that sort of relate to the third equation? The third equation was the one that said the 2A minus 11B is equal to 5, right? So what are you thinking? I'm thinking if I were to put this A over here, right, the A of 2/3, and this B over here, which is the minus 1/3, should it equal 5, right? I mean, and if it does equal 5, then what does that actually mean if it does equal 5? Well, let's first of all, let's try that out. Let's put them in. So 2 multiplied by 2/3, right? That's my A value, right? Remember the A, we worked out the A as B. And remember, this 2, let me just walk you back a little bit. The 2A minus 11B equals 5 comes from the Z component of this sum that we're doing, the sum of these two vectors. So it was 2 times A minus 11 times B, that gives us the Z component of this addition that we're doing. All right? So now we're saying we have an A and a B that we came up with. These are the scalars that we think will work. So we put that here, right? That 2 over 3 here as our A. And we put the B here as minus 11 over 3. So let's do the math and set that and see what happens. So that's 4 over 3 plus 11 over 3, right? Minus times or minus, which is 15 over 3, that's equal to 5. What exactly does that mean, though? That it is equal to 5. I'm trying to understand, and I need you to help me out here. What is that suggesting to you? The fact that the Z also works out with the same A and the same B that we used when we did this for the X component and the Y component. What does that suggest to you, right? That they are coplanar is Thomas's assertion, right? So in other words, if I took the 2/3 as my A and multiplied it by all of these numbers, and then I took the minus 1/3, that was the B value, and multiplied by all of these numbers, I do get the third vector, right? It does work out that every single part of this third vector, right, the X component, the Y component, and the Z component can all be found by just simply scaling the first two vectors. So it means that those three vectors, or you can call them points if you like, are actually, as Thomas just said, they're coplanar, right? The three vectors are coplanar and not part of a spanning set. You cannot span an entire 3 space if the 3 points sit on the same plane. It just can't be done. Okay? It just cannot be done.